Hi, welcome to Math 389. This is advanced analysis. I'm just going to make sure whoever is in the online that you can let other people in as needed. Okay. And then what I want to do now is I want to continue some of our conversations on random matrix theory. So there's a tremendous amount of algebra that needs to be done for some of this. And so I am cheating and I'm just writing down some of the key steps from the book, and then we'll discuss it. I really want to talk about why these calculations work and why these are the right calculations to do. The first question is, what do you want to study? So here are 2x2 matrices. There are lots of ways you can denote 2x2 matrices. If you were teaching a linear algebra class, this is probably not how you would denote a 2x2 matrix. How would you denote a 2x2 matrix? You wouldn't do A11, A12. What would you do? A, B, C, D, right? But of course, as you start to get larger and larger matrices, it's a nightmare to work with the English alphabet. So we'll clearly shift to something like this. And then you can always have a question of where do you want to choose the entries? And so here we're choosing the entries to be real numbers. And you might notice here that we are forcing the matrices to be real symmetric. So we have it as real symmetric as A12 equals A21. So this is not the most general 2x2 matrix. What nice properties do real symmetric matrices have? Diagonalizable. What else do they have? Real eigenvalues. So we can order them. You can talk about the smallest, second smallest, third smallest, and so on and so on. You can't do that in a general case. How many parameters should it take to describe a 3x3 matrix? Yeah, 3x3.
That's symmetric.
Yeah. Well, so let's just say general 3x3 matrix. 9. General n/n matrix. That's good. This is a 2x2 matrix, but I only have 3 parameters. Wouldn't you expect 4?
Symmetric.
It's symmetric. So we have 4 parameters for a general 2x2. That's a tuple X. But as real symmetric, only have 3. How many eigenvalues are there? Two. So what that means is there's got to be another parameter, right? So if I give you a matrix, I really care about the eigenvalues. Those are the ones that have the physical significance. But there's only 2 of them. A real symmetric 2x2 matrix has 3 parameters. What's the third parameter? What's
Similarity.
It's the similarity transformation. So we can write I always forget which way we want to do this, so I don't care if well, I'll cheat and I'll look ahead as to which way we're doing it. Okay, QAQ transpose. So it's QAQ transpose and becomes Q transpose lambda Q. So if I write it like that, I can write my matrix now as an orthogonal matrix and a diagonal matrix in this nice relationship, Q transpose lambda Q. And so Q is a rotation matrix. And so Q is going to be cosine theta minus sine theta sine theta, cosine theta, and it has 1 degree of freedom. And that adds up to 3. So in general, if A is n by n real symmetric, we want to have A is Q transpose lambda Q. How many parameters do we get from lambda? N. So we get n parameters. How many do we get from the real symmetric matrix A? So it's n times n plus 1 over 2. The first row has n, the second row has n minus 1 new things, all the way down to the last row has just 1 new thing. So we're summing the first n integers, so it's n plus 1 over 2 parameters. How many parameters must Q give us? I'm sorry? 2 over n?
N times n minus 1 divided by 2.
Good. N times n minus 1 over 2. And if you add that, it's going to add up to. So we know it has to be this. So the question is, can you give me an explanation as to why that's the number of independent parameters we have? For our orthogonal matrix.
Well, maybe it's because the columns are linearly.
So the columns are linearly independent. Good.
If you know n minus 1 alpha, you don't know minus 1. Or you can narrow down the minus 1.
Well, for the first column, you want to say you have n free values.
Okay.
But what must be true about the length of each column? If it's an orthogonal matrix. What must the length of any column of an orthogonal matrix be? The sum of the squares of the entries has to equal 1. You lose a degree of freedom.
Oh.
So when I look at my orthogonal matrix Q, so columns length 1 first has n minus 1 degrees of freedom. You might think you have n degrees of freedom for the first one. It's actually n minus 1 because it has to have the sum of the squares equals 1. What about the second column, now that you know the first? How many degrees of freedom does the second have?
1 less.
Why 1 less?
Depends on the first.
How does it depend on the first? What must be true about the first column and the second column? What's true about the columns of an orthogonal matrix? So if you take the dot product of a column with itself, you get 1. What happens if you take the dot product of a column with a different column?
0.
0. You have another relationship. So second has n minus 2 degrees of freedom as perpendicular to first. Third has how many? N minus, not n minus 2, n minus 3. And that's why it's n minus 1 over 2. We should really view this not as n times n minus 1 over 2, but n minus 1 times n over 2. We're summing the integers up to n minus 1. The last column in the orthogonal matrix is forced on you. It's got to be perpendicular to everything else, so its direction is determined, and it has length 1. So you have no choice now. Or if you want, you have choice up to sign, but I don't really care about sign. So this is telling us that if I look at a general matrix, the number of free parameters for an n by n real symmetric matrix is growing like n squared. But the number of eigenvalues is only growing like n. Where are the other parameters? They're in this matrix Q. I can write any A as Q transpose lambda Q. And so you always want to do these quick calculations to get a feel for the size, a feel for the complexity. If someone asks me which of my children do I love most, what do I say? I love them all equally. When they were young, I did not say that. It's whoever slept better the night before, they moved into first place. If I'm asked which class do I enjoy teaching the most, can I express a preference between classes as a professor? No, especially since this is being recorded, right? I'm not going to say that this is far more fun than teaching that ghastly probability class. Which do you think is more important? The parameters from lambda or the parameters from Q? Or are they equally important?
What's important?
I'm sorry?
What's important?
Which do you think really matters? The eigenvalues or the parameters from Q? It's the eigenvalues. Here we can discriminate. We don't have to say everything is equal. This is now ingrained in us in society. No, you can sometimes say you're not as important as something else. If I'm talking about people, I can get into trouble. If I'm talking about parameters, I'd like to think I'm okay to say this, but I never know. So if I'm not here on Thursday, it was lovely teaching you while I was able to. Okay, so we can definitely say the eigenvalues are the more important parameters. The Q comes from how we orient our coordinate axes. Do the laws of physics depend on how we orient our coordinate axes? That's an assumption we're willing to make. We're willing to assume the answer is no. But if I change my orientation, it should not change physics. But when I write a matrix down, you can't write a matrix down without choosing an orientation. And so if I have a certain transformation, we say two transformations are similar if they can be expressed by just changing the coordinate axes. And they'll have the same behavior. You should have seen this in terms of studying the equations of an ellipse. If the ellipse is not oriented with the x and y axis, you just rotate the coordinate axes, solve it, and then rotate back. So we really don't care about the parameters from Q. But if we write things down in coordinate form, they're there. And we have to deal with it. At the end of the day, we only care about the parameters from lambda. Those are the ones with a physical meaning. Okay. The next thing is an orthogonal matrix, a rotation by epsilon. Who are my physicists here? Are you willing to consider this a orthogonal matrix, a rotation by epsilon? Sometimes people put the negative sign in the bottom left rather than the upper right. And you can ask and see, what does this do? So, if I start off with my coordinate axes, if I take the vector, 1, 0, and I apply this, where does 1, 0 go? It's going to go to cosine epsilon sine epsilon. So it's going to rotate, theta units like this. If I take the vector 0, 1, and I apply this, where is that going to go? That's going to go to negative. So that's going to be rotating down into here, also by theta. So you can interpret this as when you apply it to a vector, it's rotating the vector theta radians counterclockwise. Some people prefer to rotate the coordinate axes rather than the vector. And so you just have to be careful when you look at books as to where do they put the minus signs. You should be trained by now to have almost Pavlovian responses when you see certain things. If I give you two functions, f and big F, what should you immediately be thinking? I'm sorry? Integrals, right? What's the relation?
Small f integrates to big F.
Yeah, small f integrates to big F. The derivative of big F is little f. That should just be instinctive to you. When you see epsilon, what should you be thinking? small, right? Can I use epsilon to be a parameter going to infinity? I could. It's perverse. You know, I'm already on thin ice for discriminating between, lambda and q. This could be enough to, really get me in trouble, right? Whenever you see epsilon, you should be thinking something small going to 0, okay? And so for general rotation matrix, I would really use theta. And maybe I should put, not just write q, but maybe write, q sub epsilon, or maybe q of epsilon, to just denote that this depends on epsilon. And now what I'm doing is I'm looking at what happens if I rotate by a very small number. So we're Taylor series expanding. And so everything comes down to e to the ix is, cosine x plus I sine x, and e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. And this gives us our Taylor series. And so we get, the cosine of epsilon is 1 minus epsilon squared over 2 factorial plus dot, dot, dot. So it's equal to 1 plus big O of epsilon squared. And sine of epsilon is going to be epsilon minus epsilon cubed over 3 factorial plus dot, 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 which is going to be epsilon plus big O of epsilon cubed. Has everybody seen big O notation? Everybody has seen big O notation. Okay, so then I'll just be very brief. F of x equals big O of g of x means for all x, sufficiently large, there exists a c such that f of x in absolute value is less equal to c times g of x. Could also do big O as x goes to 0 if we want to do something else, which is what we're doing above. So note x, 10x is big O of x squared over 1,000 factorial as x goes to infinity. And this is the one that confuses a lot of people. 10x equals big O of x over 5 as x goes to infinity. It's basically just saying the function on the left in absolute value is growing at most as rapidly as a constant times the function on the right. It doesn't mean that it's growing slower. So a lot of times when people write big O notation, in their mind, they're thinking that what's on the left is smaller in the limit than what's on the right. That's not the case. Okay, so what we're saying is that if the angle is really, really small, the cosine of epsilon is basically 1. And the error you make is on the order of epsilon squared. Sine of epsilon is really epsilon plus an error of order epsilon cubed. For those of you who've done physics, you might have seen some approximations like this when you're looking at the pendulum, where you approximate sine of theta with theta. So there's a long tradition of doing something like this. Because I have error terms, I can definitely write an equality above. And what I can do is I can ask, what is the impact of taking a matrix and acting on it by q epsilon on the right and maybe q transpose epsilon on the left or vice versa? Okay. And as a brief digression, do people remember integrating in polar coordinates? So what does dx dy become? R dr d theta. But you really shouldn't view it as r dr d theta. How should you view it? Yes. Why should you view it like that?
Because if you imagine the little curvilinear rectangle, one side has dr and the other has r.
Good. But there's a nice geometric interpretation, similar to that, or a unit interpretation. This is supposed to be an area. Right? D theta is unitless. This now is a length, and this is a length. Right? Do you remember how this is proved? Do you remember the Jacobians and all that stuff? And we have a nice change of variables. X is r cosine theta, y is r sine theta. We calculate the Jacobian. I always forget if it's with the EAN or I think it's EAN. And you look at the different partials. Is it I? I always get that wrong. Okay. Well, it's probably with an E is killing people. And so you form this matrix of partial derivatives. Right? So, dx dy is going to be the Jacobian dr d theta. And so we'll have partial x, I'm sorry, partial r, partial, well, so I mean, there's lots of different ways you can do it. The determinant is not going to change because we're going to take the absolute value. We can do partial y, partial r, partial x, partial theta, partial y, partial theta. And now when we take the absolute value, so derivative of x with respect to r, we're going to get cosine theta. With y, we're going to get sine theta. And the derivative of x with respect to theta is going to be r cosine theta. Oh, no, sorry, r sine theta. And the derivative of cosine is minus sine, so it's going to be minus r sine theta. And then the derivative of r sine theta is going to be r cosine theta, dr d theta. And that's going to be cosine squared with an r minus a minus sine squared. So it's going to be r times cosine squared plus sine squared. So that's just going to give you r dr d theta. And so if you remember your multivariable calculus and your derivatives, what's going on. Another way of viewing this is, let's imagine we have a circle of radius r, and we extend it, not drawn to scale, a little bit like this. And we're going to move, again, since I'm not drawing things to scale, let's really not draw things to scale. Let's extend it by a delta theta. And we want to calculate what is this extra area. And so if we want to calculate that, it's going to be pi r plus delta r squared minus pi r squared. And then what fraction of that annular ring do we have? Delta theta over 2 pi. And so when we expand things out, the pi r squared is going to cancel, and we're going to get 2 pi r delta r plus pi delta r squared times delta theta over 2 pi. The 2 pi's cancel, we get r delta theta plus 1/2 delta r squared delta theta. And there, do you see the r dr d theta? The r dr d theta is naturally emerging. What else is present? A smaller term. And in the limit, what happens to that smaller term? It goes to 0, but so does the other term. It goes to 0 faster, right? And so you're continuing our string of having preferences, right? The secondary term doesn't matter because it has that extra delta r. It's much, much smaller than the other term. If I divide both sides by delta r delta theta, then the first term is actually going to converge to something nice r, and the second term is going to converge to 0. So this is the main thing I want you to pull out of what you've seen before with polar coordinates and all this stuff. Okay, that when we're doing these calculations, if we want to just write things down, there is a secondary term, but it's not going to matter in the limit. What matters is that first term. Okay. All right. So now I'm claiming QAQ transpose equals the following. How do you think I got this? Just multiplied it out, right? I put an A, so just brute force. So A was going to be like A11, A12, A21, A22, and then we have Q transpose. And so it's not letting me copy it. Oh, well, all right. So Q. So Q was cosine epsilon minus sine epsilon, cosine epsilon. And so if we take Q transpose, the minus sign just goes down to the bottom. So it's going to be 1 plus big O of epsilon squared minus epsilon plus big O of epsilon cubed, epsilon plus order epsilon cubed, and then 1 plus big O epsilon squared. And then on the other side, it's going to be 1 plus big O epsilon squared, and then the minus is going to be up top, minus epsilon plus big O epsilon squared, epsilon plus big O, oh, sorry, epsilon cubed. Plus, and then the last one is going to be 1 plus big O epsilon squared. And so now we just multiply things out. And then I'm only keeping things up to order epsilon squared. If I'm only keeping things up to order epsilon squared, do I have to really worry about the epsilon cubed terms? No. So that makes life a little bit easier. So it's very straightforward. Does any part of this look reasonable to you? Can you at least do a quick check and see if I've made any obvious mistakes?
Symmetric.
So it's symmetric. So good. So sanity tests. It's symmetric. If it wasn't symmetric, I'd be shocked because we know that this is a real symmetric matrix.
It's also real.
It's real. No complex numbers have come in. There is a special case that you should be able to check in your head.
Oh, if A is identity,
I'm sorry?
if A is identity, that's something, right?
It's not A being the identity, there's something else.
If you mean
Okay, so what would it mean for the rotation to be the identity?
don't,
Right, and so what would that mean? What does that tell me about epsilon?
so 0.
Yeah. It's correct if epsilon equals 0. You just get back A. Right? If epsilon equals 0, we're not rotating. And so when we look at it, we get back the matrix A11, A12, A12, A22, because everything else has an epsilon. This does not prove that we have made no algebra mistakes, but it's at least reasonable. This is what you would expect. Okay. So we talked about random matrix theory earlier, and we talked about choosing probability distributions for the matrix elements. And one of the biggest questions in the subject is, why this distribution? Sometimes it's because I can work with that distribution. What's the big lie of Calc 2? So you leave Calculus 2 thinking you can do something you can't. Yeah, you think you can integrate. You can't integrate. Your teachers work really hard to give you cookbook problems that have nice closed form antiderivatives. In general, if I give you a function to integrate, you can't. You cannot get a closed form expression for most integrals. Sorry. Just a fact of life. We have to work really hard to give you something that you can do. We're now shifting to random matrix theory. One possibility is, let me choose maybe the probability distributions for my matrix elements that will lead to nice integrals. Okay, you can definitely do that, but is that physically reasonable? One thing is to hope that you have universality results, that things don't matter what distribution you use, as long as you take a nice distribution, say mean 0, variance 1, finite higher moments, that you'll get the same answer. And it turns out, this was not known when I started in the subject, but by the time I was at Williams for at least a few years, it had then been proved that yes, a lot of these results hold for all nice distributions. Some of the results were known from back in the 60s, held for all nice distributions, but it wasn't until much later that other related questions about the eigenvalues were shown to be independent of the distribution. So to some extent, you might want to say, let me just see what's the most general class of probability distributions we can look at. And this goes to some of the conversation we had before we started today. Can I put a space on probability measure? The other thing is to ask, maybe there's a canonical choice for the probability density. So can anybody define canonical in mathematics? So I wouldn't say, the one that people normally use is, there's a reason to use this one. This is the natural one. So frequently, often a canonical or a natural choice. And so is there a natural choice of probability distribution to use? No, why? And so that's what we're going to see today as to why it's the normal distribution. And in terms of doing the calculation, we are going to make an assumption from physics that the universe does not care about how we orient our coordinate axes. If it makes you feel better, you may assume the universe cares about you. Right? That's not going to have any impact on what we're doing later today. So if you want to add that, that's fine. I do need that the universe does not care about how you orient your coordinate axes. So we're going to assume that the probability of QA Q transpose is the same as the probability of A. Because really, I know that you are all very fortunate and you are one of the only groups of people to ever go through life with wonderful linear algebra teachers who emphasized exactly what should be emphasized. But because these lectures are being recorded and listened by people who are not as fortunate, I will state for those poor unfortunate souls that a lot of times it is not emphasized enough that what we're really looking at is we're looking at a transformation. That's the fundamental. Maybe the transformation is stretch it by a factor of 2 in this direction and squish it by a factor of 2 in that direction. And then if we want to actually compute things, we then have to choose a basis, write the transformation down in that basis. And if you want to use a different basis, what did you prove in linear algebra? You proved the change of base formula that allows you to figure out how does a matrix look in a different base. And this is our orthogonal transformations right here. It doesn't have to be an orthogonal transformation. You can do something more involved. So depending on what basis you're using, the transformation looks different, but it's the same transformation. What do we care about? Well, it turns out that the eigenvalues of the matrix are the same under the transformations. So lambda of Q A Q transpose is the same as lambda of A. Up to reordering, but we don't. So this is a nice result. Does anybody know how to prove that the eigenvalues are the same when you do orthogonal conjugation? So, theorem QA, Q transpose, and A have the same eigenvalues. So look at the determinant of QA, Q transpose minus lambda I. That's how we find the eigenvalues of a matrix. And now we do nothing. How can we do nothing?
Multiplied by Q.
Right, so this is the same as minus Q transpose lambda I. Oh, sorry, I want Q. Q lambda I Q transpose. So this is the same as the determinant of Q A minus lambda I Q transpose. So this is the same as the determinant of Q, determinant of A minus lambda I, determinant of Q transpose. But what's the determinant of an orthogonal matrix?
Multiply them together. It's determinant of Q.
So you could also do it that way. You could also say it's the determinant of Q transpose, determinant of A minus lambda I.
Yeah, but
Or you could also say, so we could do it like that. And what's the determinant of Q transpose? Just one. So this is then the same as determinant of A minus lambda I. So this shows you that the eigenvalues of A and Q transpose solve the same equation. So they have to be the same. So if I do an orthogonal change of variables, I don't change the eigenvalues of my matrix. And so if I want my matrix, if I want my transformation, if I want to study its probability, the probability shouldn't depend on how I orient my coordinate axes. And that's why I'm going to impose the condition that I want the probability of QA Q transpose to be the same as the probability of A.
so we define the probability measure of the eigenvalue.
No, we've defined the probability of a matrix as the product of the independent probabilities.
Oh, okay.
But I want it to also satisfy this property. So, and we'll have the probability of the matrix, A, B, B, C is, say, the probability A, probability B, probability C. The probability of a matrix is the product of the probabilities of the independent entries. Now, these don't all have to be the same entry, the same probability. It could be P11, P12, P22. They don't have to be the same probability. It's nice if they're all the same probability. But I could say maybe we have a different probability measure for the different entries. Maybe the diagonal is chosen differently than the non-diagonal. And initially, this is a very weak condition. I can choose any nice probability distributions. But if I want the probability of QA Q transpose to be the same as the probability of A, that's going to then put some constraints on the P's. So this constrains the PIJs. So if I want the probability of a transformation to be independent of the basis used, I can no longer just choose any probability. And this is what's going to lead to the canonical or the natural choice. Because I want this to work for any orthogonal transformation, I can no longer choose just any old probability density for each entry. There's going to be consequences. And this is what's going to lead to the Gaussian. And there's a wonderful approach to this. And this is this epsilon rotation. And I was trying to motivate this with something you had hopefully seen before with polar integration as to why it's RD theta. There really is a higher order term that vanishes in the limit. Okay, if you look over here, do we have higher order terms? Oh yeah, of course, right? Now, in some sense, if I actually wanted to do this lecture without cheating, I could. It's really not that hard. It's just time consuming and it's so likely to make an algebra mistake. So it's not illuminating for me to try to do this. But if I choose the probability of my matrix to be the product of the probabilities, then I'll say I'll use P11 for the probability of the 1,1 entry, and in a shock, P12 for the 1,2 entry, and P22 for the third, right? Then the probability is just going to be the product of the three probabilities. All right, well, now let's figure out what is the probability of the new upper left entry of QAQ transpose. Well, we saw from before that the upper left entry is A11 minus 2 epsilon A12 plus something of size epsilon squared. So what we're going to do is we want to figure out what is this? Well, we can Taylor expand. We'll assume whatever densities we're using are nice. And so we're using, so we're using P11 of X is going to be, let's say, let's do this. Let's do this right. A plus X. So we're going to Taylor expand about A. So if we wanted to Taylor expand about A, it would just be the value of the function at A plus the derivative of the function at A times X plus the second derivative of the function at A divided by, and I've made one mistake. What is the mistake I've made? No, this is fine. This is fine. And just, continuing. That should be X squared. Okay. So is everybody comfortable with this as a Taylor series expansion? So now we just have to figure out what does A equal. So for us, what does A equal? Yes.
What do we assume epsilon to be small?
Because what we're doing is we're trying to see what happens if we do like an infinitesimal rotation.
So basically, our assumption is the probability when we do an infinitesimal rotation.
No, our assumption is that no matter what rotation we do, the probability is unchanged. But if you do a large rotation, everything is going to be hard to follow. If we do a very small rotation, we can expand things. We're going to get to that in a moment. We can expand things in terms of a constant term, an epsilon squared term, and so on.
So in general, that was epsilon squared.
The only proof I know is using epsilon small. Is that if we want things to be the same, the epsilon term has to have a zero coefficient at the end of the day. Because we know the probabilities are the same, right? So we know the probability of A and the probability of QAQ transpose are equal. And we can write this as P of A plus some function, let's say fancy F of A times epsilon, plus some other fancy function of A epsilon squared plus ... And we know these have to be the same as epsilon goes to 0. They have to be the same for all values of epsilon. So imagine, if this is not 0, as epsilon goes to 0, left-hand side does not equal right-hand side. So this is the key idea that we'll lead to. And again, it's actually not bad that you had me do this now rather than in a few minutes. This is the motivation of why we're doing all of this, why we're doing this epsilon expansion. We know they have to be equal for all epsilon. If epsilon is large, then it's really hard to see what's going on. But when epsilon is really small, the first order correction term dominates the second order. And if that first order correction term isn't zero, we have a problem. Because no matter what the second order term is, it can't correct for it. And the third order can't help the second order. And the fourth order can't help the third order help the second order. They're all too small. So if the coefficient of epsilon is not zero, then as epsilon goes to zero, there's no way we can have equality. So we have equality for all epsilon. So we have equality for all epsilon. And it's useful when epsilon goes to zero. So that's the key idea here. Because this is true for every value of epsilon, as epsilon goes to zero, if the coefficient of epsilon were not zero, there's no way this equality could hold. It would be off by a very small amount. This is like saying, we were off by 15 cents in the US budget last year. Doesn't matter. I don't want to say this with the cameras rolling. No, I was just involved in something where in a multi-million dollar budget, people decided to decrease the budget by $27, $1 for every year that a program that was being cut was in existence. Did decreasing a multi-million dollar budget by $27 have any impact? No. But it sent a signal. The next day, of course, people said, well, we don't know what people meant by this. Does it make a huge difference in terms of values? No, but it makes a difference. We know that this has to be an equality. We are assuming that the probability of the transformation doesn't depend on the basis used. So if I rotate by epsilon, no matter what epsilon is, epsilon could be small, epsilon could be large, it has to be equal. It's only useful as epsilon goes to zero. As epsilon goes to zero, the epsilon squared in higher terms are clearly much, much smaller than the epsilon term. If the epsilon term is zero, what must be true about the epsilon squared term? Also zero, but I don't need to use that. Maybe that gives you some additional, I don't know. You could go through and you could write down what the epsilon squared terms are. That would be actually an interesting exercise. Go through, expand things out more. And by go through, I mean, just have Mathematica do it for you. Because you can just write it down and have Mathematica tell you how many terms you wanted to keep, expand things out, do all the simplifications. So when we do this now, we want to use our formula to Taylor expand about A. So for us, what does A equal if we're doing the 1, 1 term? A equals A 1, 1. And for us, what does X equal? So minus twice epsilon A 1, 2 plus order epsilon squared. And so if you look, here's the, oops, let's do it in green. Let's do it in green. Here's the PA11, and here is the PA11, exactly as we would expect. Now for the next term, we're supposed to have the first derivative at A times X. And here we have the first derivative at A times X. And notice we have the minus 2 epsilon A12, the minus 2 epsilon A12. But of course, we also have this part over here. Well, that just becomes this part over here. And that epsilon squared includes a lot of things. It includes the first derivative of P11 times all that stuff. So is everybody comfortable with how we get the first line? Of how we get this line by Taylor expanding? Once you give me that, do you agree that it's essentially the same kind of analysis to get the second line and the third line? We're just taking these functions and we're Taylor expanding. And since we only care about the epsilon squareds, it's clear that we're expanding each of these about, the point A11, A12, A22, and that's why you see those over here. And we're only keeping the first order correction terms. Okay. So now that we have that, we can now calculate what is the probability of Q A Q transpose. And this is just go through, take your matrix, take the Taylor series expansions and multiply, and only keep terms up to order epsilon. Right? So do we all agree that this is just trivial algebra? So it's basically, P11 of, I'll call it QA Q transpose 11 plus, I'm sorry, times P12 QA Q transpose 12 times P22 QA Q transpose 22. And then we Taylor expand each one of these. So it's nice plus epsilon squared plus dot dot dot. Same. And we combine all of those to nice plus epsilon squared plus dot dot dot. So it's just algebra. Now, when you look at this, does anything jump out at you as, boy, that was nice to see that? Okay, good. So we have a nice, easily identified, epsilon term. That whole thing there. And I guess I'll draw it like that. So we have a nice epsilon term. Good. But what else do we have that's nice? Yeah, what's that constant term? That's just P of A, right? We're trying to show that, P of, QA Q transpose has to equal P of A. Oh, look, there's P of A, right? So it's starting off with exactly what we would want. And now, what's the only way that this can equal P of A as epsilon goes to 0? Yeah, so the thing in square brackets has to equal 0 if want this to be P of A as epsilon goes to 0. If the thing in square brackets wasn't 0, then as epsilon goes to 0, it's not going to work.
Why? Well, you can still work. Right?
No, because the epsilon squared term is not going to be large enough to overcome an epsilon term. Let's say the thing in square brackets is 1/1,000,000,000.
Yeah.
Then this is supposed to be a full equality. It's supposed to equal PA. If the thing in brackets is 1/1,000,000,000, as epsilon gets really, really small, the epsilon term is going to be of size epsilon over 1,000,000,000, and the epsilon squared term is going to be much, much smaller than that. You won't have an equality. You'll differ by a little bit.
Oh.
So have epsilon be like 1/1,000,000,000 to the 10 billionth power. Then the epsilon squared is going to be so small, it can't overcome your epsilon term. And they're not going to be equal. So we have, let's say we have, P of A equals P of A plus some constant epsilon plus, some function of A times epsilon squared. And this is true for all epsilon. Well, both sides have a P of A. We can subtract that. So we get 0 is equal to C epsilon plus G of A epsilon squared. What can we do to both sides? Divide by epsilon. So then you get 0 equals C plus G of A epsilon. So if epsilon is sufficiently small, false. So there's no way that this could be equal. So remember, this is true for all epsilon. So if it's true for all epsilon, the only way it can be true for all epsilon is if the coefficient of the epsilon term is 0. Because we can subtract the P of A from both sides, and then we get 0 equals some constant plus G of A times epsilon. And once epsilon is sufficiently small, what's sufficiently small? So this is your chance to impress me with your real analysis. Epsilon should be less than what? So give me a bound that works. Well, show me that this can't hold if epsilon is sufficiently small. Give me a value of epsilon that would work. Well, don't you think, well, what should your bound depend on? C and what else? G of A. So give me a bound depending on C and G of A. Almost. You made the classic mistake. Nope. Plus one. What if G of A is 0? Right? No, and this is important. You know, this is not emphasized enough in classes other than the real analysis classes you took, right? In other people's real analysis classes, they often don't remember to put in that plus one, because what if G of A is 0? And so if epsilon is less than that, then there's no way, and we'll do this in absolute value, then there's no way that that term can overcome the C. Does this make sense, or you still?
Yeah.
Okay, so the only way we can have an equality for all epsilon is if the epsilon coefficient vanishes. If epsilon is large, then the epsilon squared term can actually impact the epsilon term. But if epsilon is really small, the impact is insignificant. No offense, this is like we all decided, you know, we're going to stand up, help our country. We're going to help America. We're all going to throw in 50 cents to pay off the national debt. No noticeable impact. Okay. The epsilon squared term, it just doesn't matter. It can't do anything to the epsilon term.
I think potentially if you had an absolute value around GA.
Well, no, G of A is just some function that depends on A.
Yeah, what I mean is in the epsilon value.
Oh, sure. Yes. Yes, good. We should definitely have an absolute value G of A there. Yes. Okay. So now going back to what we have, so we all agree that the only way this can work is if the bracketed quantity equals 0. Okay. So when we look at the bracketed quantity equals 0, okay, that's basically what we have over here. This is just rewriting things a little bit. And so for the bracketed quantity to be 0, that's equation 17.9. So I just rewrote the bracketed quantity. But notice over here, we have something that's very nice. This piece only depends on A11. What about this piece? Oh, wait a minute. Oh, sorry. No, that's not the case. Sorry, wait a minute. Sorry, it's the next line. We rewrite things a little bit, sorry. When we rewrite it over here, what can you tell me about this piece? Right. Only depends on A12. What can you tell me about this piece? So I can keep varying A12, and that doesn't change the thing on the right. I can vary A11 and A22, and that doesn't change the thing on the left. What's the only way? So this is some function. This is some function of A12. This is some function of A11, A22. What is the only way a function of A12 could be the same as a function of A11 and A22? Constant. They have to be constant. This can't have any A12 dependence, or if I change it, then that changes the right-hand side. So it has to be a constant. What should we name that constant? C. No, we've already used lambda. I mean, it's debatable if I can use F and G because we've used F and G so many times, but
I thought we already used C all along. Too. We were using C a few slides ago.
I don't think so.
The example.
Go down.
Or do,
Go down. Go down.
yeah, okay, yeah, that's just an example for just explaining to you why it only mattered for the epsilon. This is an aside. Okay, so we agree that it's a constant, and we're going to let that constant be C. So because that's equal to C, the left-hand side is the easy one to solve. We just take this expression, we set that equal to C. We can move the A12, P12 to the other side, and we get the derivative of P12 is minus constant A12 times PA12. That's the Gaussian. If I have an e to the negative x squared, when I take the derivative, I get, some constant times x times e to the negative x squared again. So when you do this, it's telling you when you do the differentiation, you're going to get a Gaussian. Now, which Gaussian are you going to get? This is a degree 1, this is a first order equation. This should be a degree of freedom. But it's a probability distribution, so you lose the degree of freedom. It's a probability distribution, lose the freedom as must choose normalization constant. So integrates to 1. I do realize we're going to go over by about a minute or two, but if you have to leave, by all means, completely understand. So we choose the normalization constant, so it integrates to 1. Because again, there's lots of different functions that work. I could take the function, I could multiply by 5, by 16, by 1/3, by -5. Any of those work, but it has to integrate to 1. So that's where you lose that degree of freedom that you should have from a first order differential equation.
By the way, we still have 2 minutes. We have 2 minutes.
Oh, we have 2 minutes?
10 minutes.
Oh, we have 10 minutes. Oh, we have till 12:35. Oh, okay.
Spring break.
It's spring break. Yeah, it's good. It's good. David, I mean, I thought I had prepared enough so that we'd be able to finish. How am I so off? Okay, now I feel better. Okay. So what you should have said is, Professor Miller, we should be done now, but we're so excited and we're loving this so much that for you, we'll stay an extra 5 minutes. And then you get out of 5 minutes. Okay, so now we analyze the right-hand side, but is that going to be hard? Well, if you look at what's going on now, it's really nice in terms of how things split. So this is supposed to equal a constant. Can we come up with nice ways of breaking it? So the thing in green has to equal that constant C. All right. And so unfortunately, it's a little bit more involved now. But what can you tell me about the left-hand side and the right-hand side? So we'll do new colors. We'll do orange over here. What can you tell me about this? Yeah. Only depends on A22. And we haven't used William colors. Only depends on A11. So both of those have to be a constant. And this time, we will write the constant as CD. Why CD? Because I know the answer. So by writing it as CD, it just makes the algebra work out a little bit nicer at the end of the day. Okay. You could have just called it D. That would have been fine. Okay. And so we now solve and we get a very similar equation as before. And so when the dust settles, it looks like a Gaussian. And then if you want things to have mean 0, then that forces D to be 0. But this is remarkable. And okay, so I guess I didn't put down anything. But so now we actually have the known values. So if we want the probability of QA, Q transpose to equal the probability of A, and we want the probability of A to be P11, A11, P12, A12, P22, A22, then the P's are Gaussians. So this is where, if you've ever heard the phrase Gaussian orthogonal ensemble, this is where it's coming from. I'm sorry? Unitary is when we're dealing with complex Hermitian matrices. And so, you can do similar calculations. Now, it's worth noting that, oops, that when you, oh, now I gotta redo it so it gets in the right spot. Okay, there you go. It's worth noting when you look at this, we've got minus CA11 squared over 4, but on the previous slide, we had CA12 squared over 2. So they don't have the same variance. On the diagonal, the A11 and A12, the variance is 2. On the off diagonal, the variance is 1. What's the difference between the diagonal and the off diagonal?
The diagonal has 2 separate values. The off diagonal has 1 distinct value.
Yeah. Another way of looking at it is, if you're on the diagonal, you only show up in the matrix once. If you're on the off diagonal, you show up twice. So just rephrasing what you said. That's what's going on here. And in some of these other random matrix ensembles you can look at, you have to take into account that not every element is occurring the same number of times. And so you might do certain things so that each quantity has the same impact. So we have now come up with a canonical choice for 2x2 matrices. What about n by n matrices? Who wants to look at an arbitrary n by n matrix, look at an arbitrary orthogonal rotation matrix? Now, the number of degrees of freedom for that arbitrary orthogonal matrix is going to be n minus 1 times n over 2. That's a lot of epsilons to keep track of. All those epsilons have to be 0. Is anybody gung-ho about this? How do we get around doing this? What do we say?
Wave our hands.
Good. So we wave our hands and say, without loss of generality, it was sufficient to do what we did today. Why is it sufficient? We do a sequence of infinitesimal rotations with just 2 of the variables. And you can play this game just for 2 indices I and j. And then you show that it has to be like this. So again, in your linear algebra class, I'm sure they talked about sequences of elementary matrices, that if I want to get to something, I don't go directly there. I do it through a sequence of nice, maybe row exchanges, or adding a multiple of this row to another. And by doing a string of elementary matrices, I can bring my matrix into this nice canonical form. It's the same thing here. So we do it for 2x2. So do for 2x2, general n by n, apply these for all the pairs ij. So we don't have to write down a general n by n infinitesimal rotation with all those degrees of freedom. It's enough to do this one simple case. One thing you have to be careful about is sometimes if you do too simple of a problem, things look nice. If I want to calculate the eigenvalues of a 2x2 matrix, can I write that down? Can I solve it? What kind of equation am I going to have to solve? Quadratic. Can I solve a quadratic? Yeah. 3x3? If I had to, can I write down the roots of a 3x3? Of course. 4x4? Yeah. I'm not having fun, but I can do it. But once I hit 5x5, I can't do it anymore. I can't write down a closed form solution. So we can actually write down the distribution of eigenvalues of the 2x2 Gaussian orthogonal ensemble because it's a quadratic equation. We can't do that for the n by n, and you have to develop new techniques. And this is a great thing to end on, that sometimes a calculation can be too simple and can mislead you as to what you can do in general. But today, it's a tough concept, but it's a wonderful concept that if I have a chain of inequalities that hold for all values of a parameter, if I can send a parameter to 0 and I have an expansion, the only way it can stay true is the constant terms must match, and then the coefficient of the epsilon term must be 0. Right. So this is a good place to end. And that ends at the right amount of time. So now I feel better.